gamma 1, gamma 2, gamma 3 are all unknown terms, then how many to know omega? How many terms do we have to know? We have to know 1, 2, 3, 4. We have to know what is gamma 1, gamma 2, gamma 3. So how many terms do we need to know? 7, right? But how many data points do we have? 4, E1, E2, E3, E4. And so therefore we can never really know what is omega. Because we need to know 7 things, we need to solve for 7 variables in 4, and we have got 7 unknowns and only 4 equations to solve them for. Right? And therefore really there is a problem here. We can't really never figure out what omega is without making more assumptions. Okay? One convenient assumption, there are 2 convenient assumptions which you make to solve this problem. One convenient assumption is to assume that all the sigma square i's are the same. That the variance of the error term is constant throughout. So this will go, this will go, this 2 will go, this will go, this will go, right? Makes the problem little bit less complicated. Because now we need to know gamma 1, gamma 2, gamma 3 and sigma square, 4 quantities and 4 variables. Right? But the problem is if you increase the data points, then the number of quantities to be estimated will also increase in the same way. Right? So it doesn't really help us that much. Therefore we make another assumption. Another assumption we make is gamma 1, gamma 2, gamma 3 are all 0. That is called the assumption of no autocorrelation. The assumption that sigma 1 square is the same as sigma 2 square is the same as sigma 3 square is the same as sigma 4 square is the assumption of no heteroskedasticity or the assumption of homoskedasticity. Right? Whereas if you put all these to be 0, so this becomes 0, 0, 0. Yeah? Then under this specific assumption example, under these 2 specific assumptions, omega takes a very specific form. Omega takes a very specific form. Omega is sigma square into the identity matrix. Right? Omega will be sigma square into the identity matrix under these 2 specific assumptions. If we don't make these assumptions, then of course we have to deal with another omega. Right? So please remember that. We will learn to relax these assumptions later on. Okay? And we are going to replace the various values by learn how to replace the various values by their estimates. And then plug that correct omega in there. Right? Okay? Which are called robust standard errors. But at the same time, at the moment we are making this assumption sigma square I, therefore the rest of the development is only as valid as these 2 assumptions. Okay. Now from this I know, now so far what do I know? I know that expectation of is equal to yeah. Under my very specific assumption, omega becomes sigma square I. Okay? This becomes yeah, or to write things here, this becomes sigma square x dash x inverse, yeah? Sure? Sigma square will come out. Sigma square I can be taken out. I just write it as sigma square now. Okay? And you get x dash x will remain there. So this will become the identity matrix again. X dash x into x dash x inverse will be the identity matrix. So this will become sigma square into x dash x inverse, right? Variance of beta hat becomes sigma square into x dash x inverse. Variance of beta hat becomes sigma square into x dash x. Now this is a simple generalization of the formula. For a univariate case, we say yi is equal to beta xi plus ei, right? What is the variance of beta hat? Sigma square upon summation xi square. But if x is just a column vector, then x dash x is summation xi square, because x dash will become a row vector, x will become a column vector. So what we are really saying is x dash x inverse will become 1 upon summation xi square, and sigma square will be there. So that same formula is being generalized again, sigma square, right? Okay. But for a multiple linear regression model, now let's see what this really means. Okay, let's try to bring this down. So we know, now let's try to look at the details of this. Okay. So the variance of beta hat is sigma square x dash x inverse. Okay. So suppose I have x. Suppose I have x. I have the x matrix. Suppose my x matrix is 1, 1, 1, 1, x1, x2, x3, x4. Right? Suppose that is my x matrix. Now, so what is x dash x? X dash x we know for summation xi, I goes from 1 to 4, summation xi, I goes from 1 to 4, yeah? Now in general, instead of 4, I will make it n, okay? Just did 4 because you can actually work that matrix out and see. So this will be x dash x, n, okay? Now we want the inverse. We want the inverse of x dash x. For that, the first thing that we must get is the determinant, right? So the determinant of x dash x that is the determinant of x dash x, yeah? We know that this is nothing but n square into variance x, right? Because we know that if you divide the determinant by n square, you get the variance of x. Is that clear to everybody? Sure? Some faces are looking uncertain. Clear, huh? Okay. But this is what? This is n square. Therefore, this becomes, yeah, n summation xi minus x bar square. The determinant of x therefore is n into summation xi minus x bar square. So my x dash x inverse matrix becomes, so my x dash x inverse matrix becomes, x dash x inverse matrix becomes, so first I will write summation xi square upon n, yeah, that is the first element, right? Then the second element becomes minus summation xi, so I get yeah, this becomes yeah, and this becomes okay, right? Now if I multiply that by sigma square, then each of these elements gets multiplied by sigma square. There has to be an n here, right? Okay, each of these elements has to get multiplied by sigma square. So this becomes this n will go with this, right? Now what is this? This is the expected value of beta hat minus beta, right? But what is beta hat minus beta into beta hat minus beta transpose? Right, now let's understand what that matrix is. Okay, what is beta hat minus beta transpose? Beta hat minus beta into beta hat minus beta transpose, right? This is equal to alpha hat minus alpha into okay, sure. This is what? And remember, we are taking expected values of both sides. Expected value of this whole thing, right? This will be what? This will be first expected value of, so alpha hat minus alpha square, that will be the first term, first row into first column. Then you will get here expected value of alpha hat minus alpha, if I rub this out, beta hat minus beta, right? Here you will get expected value of alpha hat minus alpha, beta hat minus beta, right? And here you will get expected value of, sure? So this is this matrix. Now what is this quantity? Variance of alpha hat. So I will write here sigma square alpha, right? So this quantity will become sigma square alpha. What is this quantity? Covariance of alpha hat and beta hat, right? Sigma square alpha hat is what I should write here. This becomes covariance alpha hat beta hat, because alpha hat and beta hat are random variables, so we are going to have covariances. This becomes sigma alpha hat beta hat, and this becomes square p. Now you see the variance that beta hat that you got was the same formula that you got previously. What is variance of beta hat? Sigma square beta hat is nothing but sigma square upon summation xi minus x bar square, right? What is the variance of alpha hat? Sigma square summation xi square and summation xi minus x bar square, and these are the covariances, right? Now, so what do we know now? We now know that if you are just looking at beta hat, this individual beta hat, right, the coefficient of x as against the whole matrix, right, then you can easily show, okay, you can easily show, in general what are we saying? In general we are saying that the matrix beta hat is normally distributed with mean beta and variance sigma square x dash x inverse. This is a distribution of beta hat. Now if by beta hat you mean the whole matrix, but if by beta you mean just the coefficient of x, then this becomes relevant, right? So beta hat as the coefficient of x, please remember there is a distinction here, right? I should have made the distinction earlier, but that would have made too many symbols, right? So just remember, when I say this is the coefficient of x. In alpha, y is equal to alpha plus beta x. Whereas I have also written beta as the whole vector alpha and beta. When I mean the vector, I mean this. It involves a matrix. When I mean just a single coefficient, I will write beta yeah? Sure. Of alpha hat and beta hat. That's okay. Alpha hat and beta hat can be negatively correlated. Yeah, but that depends upon what the sign of summation xi also is. Yeah? Okay. Is this clear, friends? Okay. Now, let me do a concrete so now, from which the following follow. Why is this important? Can I wipe this off? This clear to everybody? Right? Okay. So, suppose now I want to take a test of hypothesis on beta hat. That is, my null hypothesis is beta is actually equal to some value beta star. Okay? Means the alternative beta not equal to beta star. Right? From this, what do you have? You have beta hat minus beta, right, upon sigma square upon summation xi minus x bar square must be a standard normal with mean 0, variance 1. What is the null hypothesis? Beta is equal to beta star. So, under the null hypothesis, this quantity must be a standard normal with mean 0, variance 1, right? So, suppose if I do a regression, right, and if I find beta hat to be 0.5, okay, and somebody has told me that sigma square is equal to 4, right? And from my data, I have summation xi minus x bar square as 16. Okay. Then, suppose I want to test the null hypothesis that beta is actually 0. What do I mean by testing this null hypothesis? Because I know that beta hat is a random variable. So, it has a normal distribution, right? This is the mean of beta. So, this is beta. So, what it says that if I have a standard normal distribution which has mean value of beta, I can see values of beta hat different from 0, different from beta, with probabilities given by this axis. So, it is possible, for example, that I will observe a value greater than beta, a value of beta hat greater than beta, or a value of beta hat less than beta.